Okay, we're recording now. And then, as I said, sea level drops off and erosion rates creep up. This is reflected well in the Cretaceous, and because of this, is something I've never said before. But now you'll notice where we have lots of strata preserved in Alberta, like the Devonian strata, the Mississippian strata, and not to a lesser degree the Pennsylvanian, but certainly the Permo-Triassic. We have a lot of strata preserved because sea level's going up, and these global high stands are actually mapped on the basis of these strata being present on all of the continents all around the world. And so, you know, now we can expand on this concept a bit as you become more and more comfortable with it. But the idea that Larry Sloss had was that these were globally correlatable or correlative oceanic sequences. And I'm running out of space. Oceanic sequences. And what's driving these is probably on the largest scale tectonics, but there's certainly influences of sea level that happen on a much more high frequency kind of scale because global ice caps, or I should say polar ice caps, tie up a lot of the Earth's water and can change sea levels in of itself by almost 200 meters, so right around that. So there's enough of, there's certainly more than one or two factors at play for what's dictating global sea level. And as you can see now, actually, we're kind of just coming out of a global low, and that's because polar ice has been tying up a lot of our global waters. Just a quick look at global Cretaceous paleogeography. This is kind of a cheat on my part. Rather than put in the reference, I just put the title of the paper and the authorship and its source. It's a little quicker when I'm putting a lecture together to do this. And it's not great form, but it's not terrible. At least we're giving credit where credit's due. And these gentlemen, no, these colleagues, I shouldn't say gentlemen, that's rather sexist viewed things, especially since one is clearly a woman. And this is the Cretaceous Earth here in their view of it. And their view is not that different from what pre-existed for views of paleogeography. It was this general idea that the continents are starting to move apart. Africa is moving one direction, South America moving in another direction, with a rift in between them, and that rift has got a set of spreading zones. And so the proto-Atlantic Ocean is starting to develop. But their view of things is that a lot of the northern continents are held together for some time, and there's still a relatively large landmass that's kind of a polarish landmass that includes Asia, North America, and Europe that are all kind of conjoined. And then you can see down in the south are where Australia is. It moves to the north over time away from Antarctica, and I've kind of drawn that arrow the wrong way if you want to take it that way. What I should do is maybe just say that this is moving a small amount that direction. This is the Indian subcontinent. It's starting to launch itself to the north. And this is about 100 million years ago, which interestingly is just after the time that the first Cretaceous deposits are deposited in Alberta. Okay, before that is an unconformity. And so the oldest Cretaceous rocks in Alberta are probably about 112 million years old. Remember, the Cretaceous goes back to the 140s, 145 million years old or something like that. So, you know, there's 30 million years of stratigraphy and time that are missing for the Cretaceous. So we're kind of starting the Cretaceous record in Alberta at the lower part of the middle Cretaceous. Which I didn't say specifically for the Devonian, but that's what happened then too, because of the presence of an unconformity. This is showing the presence of seawater as white. In other words, if we were to color the ocean water, you can see there's an inland sea that's starting to cross North America. This is all ocean. This is all ocean. And North America is also not connected in any way to South America. And that, in fact, doesn't happen until quite a bit later. But you can start to see some things here that are paleontologically significant from the point of view of migration of fauna. South America is more or less isolated. Australia and India are isolated at these times, coming separate from Antarctica. And yet Europe and Asia and North America are in proximity to each other. And you see that in the distribution of fauna and to a lesser degree flora in the Cretaceous record. And so paleontologists have some luck kind of predicting what continents were together and confirming these models by looking at distributions of dinosaurs. And many of you probably know that Phil Currie is a fairly celebrated dinosaur researcher. He's a professor in biological sciences at the U of A. And this is, those are the types of questions that they like to answer by looking at populations of ancient animals as opposed to specific individuals. We can go a little forward to 80 million years, and you can see that ocean sea levels are a little bit higher. There's less land mass exposed. There's more shallow sea. North America, and of great interest to us, Alberta, has a seaway that is quite continuous all the way from Edmonton to, well, really from Inuvik all the way down to Texas. And we think that was a bifurcated seaway that went to Canada's, what is Canada's north, but it wasn't as pointed as north back then. And so North America was in large part occupied by a shallow sea, and that's pretty well evidenced by the stratigraphy and its rock record and fossil record. Just fixing something on my screen here. And so this affords us an opportunity to look at the paleogeography of Alberta, specifically throughout the Cretaceous. And we're going to look at about 2 different time slices. And the one time slice is about from 110 million years ago. And I'll draw a shoreline here. What color shall I use? Yeah, green will work. And to set up your paleogeography, the first thing you have to know is that the ocean, as global sea levels are coming first, as global sea levels are increasing, the oceans encroach on Alberta first from the north. And that's what's known up in the Northwest Territories in northern Alberta initially as the Boreal Sea. And the Boreal Sea is becoming established, and this is all a shallow sea. And in Alberta, there's basically 3 drainage systems. And let me start by saying that there are mountains here now because the Columbian orogeny has occurred. So there's a mountain belt here. It might be, broadly speaking, looking like a peninsula or a set of large Japan-like islands. Well, there were no volcanoes, but never mind that. Anyway, it's certainly a mountain belt that's at the edge of North America at the time. And the Boreal Sea is making an incursion to the south. And there's 3 valleys that are present. that the ocean starts to flood into. And these are riverine valleys and structural valleys that are topographic lows that the seawater enters first. And this one that's most west, kind of right in front of the Rocky Mountains, the incipient Rocky Mountains, really, not quite our Rocky Mountains yet, but they're somebody's Rocky Mountains. And there's the Spirit River Channel. And then a little to the east of that is an inlet that noodles around. Kind of like that. This isn't an exact map, don't get me wrong, but it has kind of a dog leg in it. And that's the Edmonton Channel. And it kind of goes under Edmonton, which is how it got its name. So we'll call this the Edmonton Channel. And the Edmonton Channel and the Spirit River Channel, and finally this one here, which goes off into Saskatchewan, is the McMurray Channel. And that's where the McMurray Formation ends up. And this is where we start to get into the reason why stratigraphic relationships can be really difficult to interpret in the rock record, right? And the Cretaceous of Alberta is a pretty nice example of that. In that we can have sediments of the same age in the McMurray Channel, in the Edmonton Channel, and in the Spirit River Channel. And in fact, we do, but we give them different names because we can't necessarily demonstrate how they relate to each other. So in the McMurray Channel, we have the McMurray Formation. And in the Edmonton Channel, we have the blue sky on top of the Gething Formation. So we think the Gething is equivalent to the lower part of the McMurray, and the blue sky is equivalent to the upper sky, the upper part of the McMurray Formation. But we don't actually know that. It's difficult to prove. And then over here, the sedimentary couplet is really the Catamount Formation. Which is underneath the Gething Formation. Implying in a way that the Gething Formation in the Spirit River Channel has more to do with the blue sky in the Edmonton Channel than it does the Gething. And again, we don't actually know the answer to that. I would put a little asterisk here that the Gething Formation is one of the most problematic stratigraphic units in Alberta, in that it's applied to almost everything that's non-marine, sand-rich, and lower Cretaceous near the unconformity. So the Gething Formation is something that a stratigrapher would call a garbage bag term. People just stuff things into the garbage bag when they want to get rid of them. And so the Gething Formation, even though the implication here is that the Gething Formation is the same in the Spirit River Channel as it is in the blue sky, that's nonsensical, really. It's not really true. Yeah, so that's what the world looked like in Alberta. And then, of course, this is all land. So this is all dry land, and it's the home of dinosaurs and turtles and alligators and freshwater fishes and trees and grasses. Grasses are just evolving, really, at this point. We're going to change it up to about 80 million years ago. And by the time we're 80 million years ago, our shoreline, I'm going to just say, we don't know exactly where it goes in that direction. We kind of do, but it's superfluous. This goes all along there. This is a seaway now that runs to the USA, so all the way to Texas. I think you could take a speedboat to Houston if you had one at the time. And then there's a shoreline that we know it's coming from this direction, and it goes off in this direction. There's definitely a drainage here that's related to the ancestral rivers of the McMurray Formation, but it does narrow back in Alberta, and it gets quite narrow in Montana, Wyoming, before it broadens out again towards the United States. But we'll just look at this. And so this now, for a little while, things come and go, sea level goes up and down, shore faces, shorelines come and go, deltas come and go. And so we have a lot of stratigraphic units that we're going to cover next, going through as we draw the stratigraphy of the Cretaceous. But I would point out that there's units that are really important that happen at different times. There's linear sand ridges that form pretty big oil fields. These build out that way, these build out that way. And these are shore faces like the Cardium and Viking formations. But they occur at different times. The Viking formation is older and therefore below the Cardium, but sea level goes up and down and up and down, so we get these different units. So the Cardium and Viking are kind of two of the most celebrated shore face units of the Western Canadian Sedimentary Basin, but they're surely not the only one. Up here, we've got a big wedge of sediment that's coming off the incipient Cordillera, and there's fairly large deltas. This happens close to 80 million years ago-ish, and that is the Dunvegan Formation Delta. And so these deltaic units are building up. And it's not the only delta, but it's only really big one I can think of in Alberta. There might be some other, like, the Medicine Hat and Lee Park Formation. Some people, including my grad students, have written papers interpreting them way down here. I'm going to erase that in southeastern Alberta, the Milk River Formation as a very mud-rich delta, but not everyone accepts that. They think because it's mud, it must be deep water. So I think there's other deltas, to make a long story short, but the Dunvegan Formation is one we can be pretty sure of. And then we go up higher, and there's a stratigraphic evolution till finally, owing to global sea level and tectonics and whatnot, sea level starts to fall, and Alberta becomes emergent again by the time it's about, 72 million years ago. So the sea all disappears in a few million years. And that leaves us with the Belly River formations that culminate in the Scollard Formation, which is just a continental formation that forms that's present at the end of the Cretaceous and records the Cretaceous Tertiary or Cretaceous Paleocene boundary. Now, we looked at this cross-section once before, and this is a cross-section of Alberta based on real data. And now we can take a closer look at that yellow bit, which is, strictly speaking, the lower Manville. But the lower Manville is the lower part of the Cretaceous in Alberta, and then the upper Manville is the upper part of the middle Cretaceous, and then we have some Colorado group that we're going to talk about in a bit, and later late upper Cretaceous strata. So you can see that they're all deformed or pushed down into the foredeep of the Foreland Basin themselves. But I want to emphasize again this subaerial unconformity that forms at the base of the Manville and has an angular relationship or angular unconformity with the Jurassic, the Triassic, the Mississippian, which is the Rundle, right? The Banff, which is the Rundle, and the Devonian, whoops, because it goes down here. All right, though getting into the details, that's pretty neat, right? And what you can see is that these units here, the Banff, for example, in the Winterburn is basically, for all intents and purposes, well, it doesn't matter, but this is Palliser in the mountains, just so. I spelled it wrong, damn it. So that's the same as Palliser and mountains. Doesn't matter. Point being that, look, these are, the Banff is hard to erode. It's what geologists call prominent. And so it forms a ridge. Okay. And there's different ridges in Alberta. The Banff Rundle Ridge is important. The Grossmont Winterburn ridges are important. The Grossmont is basically Leduc Formation, for lack of a better term, Leduc Cooking Lake. So you can see those ridges, and they influence how the Cretaceous, especially the lower Cretaceous units, are distributed. And that gets us back to our initial paleogeographic map. Where you can see that we have the Spirit River Channel, the Edmonton Channel, and the McMurray Channel, and they're separated by these ridges, and that's why they exist in the first place. So that's the explanation for the paleogeography. You can take a closer look at this, and I've got to be honest, I've seen this diagram before. Fred gave this diagram to me, and I couldn't find a reference to it, even though I've seen it before. So it's unreferenced in here, and I've got to figure out where it's from, because it's actually a really cool diagram. This is kind of a different vertical exaggeration from the last diagram, and you can see some of the things we mentioned in the last diagram. The Rundle group, the Banff group, Wabamun, Winterburn, and here we have these important McMurray units. And some of them I mentioned already. Here's the Cataman. So the Cataman is a conglomerate that was deposited. And this stratigraphy is so good, I decided not to redraw it for you. We're going to pick up the stratigraphy on the next page for everything above this, but this is going to be our stratigraphic diagram for the Cretaceous for this lecture today. The Cataman Formation is a gravel, and you'll remember the Cataman Formation is filling up the Spirit River Channel when we're close to the mountains there. And I should pick red actually. And the Cataman Formation, because it's a conglomerate unit, it cements really hardly. When it's folded in these mountain belts, it builds a lot of fractures in it. And because of that, in the Foreland Belt, it's actually a gas play. So it's a pretty common gas play, less common oil play. So the Cataman Formation is definitely that. And when you think of sedimentary environments, and I'm going to watch the chat line here in case one of you doesn't know what this is, but we would think of the Cataman Formation as sets of braided channels. Fluvial channels, rivers, and alluvial fans. Gravelly sheets. I'm checking the chat to see that nobody is confused by those terms. I'm pretty sure you'd be introduced to them in your earlier course, but just in case. Okay, so that's understood. The Gething Formation next is not that popular an oil and gas target. The Gething is generally thought of as a fluvial deposit or set of fluvial deposits. So the Gething is fluvial, meaning river channels and depositional environments that are associated off channel with the Gething. So, you know, like overbank, we call it, you know, just sediment that spills out of the channel during flood and is deposited adjacent to channels, levees, even stuff like that. There is oil and gas exploration in the Gething, but it's not everybody's favorite. It's complex, geologically speaking, reservoir quality is variable. And there's that blue sky unit there. And the blue sky unit is interesting in that in some places it's, I mean, for the most part, we're going to call this a shore face, okay? And it actually is an economically significant unit. For sure, there's areas in northwestern Alberta where it's a gas play in what we call the deep part of the basin, the deep basin. And if you go to the area of Peace River, the Peace River oil sands, the Peace River oil sands are all in the Blue Sky Formation. So the Blue Sky Formation has actually important volumes of oil in it, like 100 million barrels of bitumen or something like that. It's more like 80 million or something like that, but it's a good number. It's substantial. And that's heavy oil. And of course, it's produced in Alberta. So that's the Peace River oil sands. You might just make a note of that because it's an important economic target in Alberta. So we'll just go Peace River oil sands. Okay. And then as we go further to the west, you get into the McMurray, right? The McMurray at the lower part. And that McMurray unit is, of course, an oil-rich unit. Now, that's not to say that there's no gas production out of the McMurray, because there is. But the McMurray oil sands are big. And so in place, there's about 1 trillion barrels of oil. So by about 4 or 5 times the biggest oil deposit in the world. What's estimated to be recoverable in that is more, estimates range between 100 million barrels and 200 million. Basically 146 billion barrels and 200 billion barrels that's recoverable in the McMurray, and about 1 trillion in place. So by far the biggest deposit. But as far as recoverable reserves are, only the second or third biggest deposit in the world as far as what we think is recoverable. The Clearwater Formation.
Murray, can I just ask a question about the
Yeah.
So in this cross section, it looks like the oil could not have migrated up dip because the sandstones there are cut off against that ridge of Rundle Dam.
That's actually a question that is kind of made. So I'm going to just walk the students back through that a little bit, Stephen, because that needs a little walk back, but it's a good question. And first I'll point out that remember, we've suggested in the course that the oil comes from the level of the Winterburn woodbed in the McMurray. So there's three sources available, Steve. One source is the Duvernay source. Okay, so that's a feasible source. But one thing we know is there is Mississippian source rock from the Exshaw Formation that made it into the McMurray, and that's known from biomarkers, okay? And then we also, from biomarkers, there was work done in a thesis 18 years ago that showed that Jurassic rocks of the, oh, I did that wrong. Jurassic rocks were also a source, and they have to come up like that, right? So that's, I'm showing the class here, by the way, arrows that are green that are showing the potential source rocks that charge the McMurray Formation. The Devonian one is Duvernay, the Mississippian one is Exshaw, and then we haven't talked about the Jurassic one that's called the Poker Chip Shales, okay? And Stephen's question is, how did the oils get past that? And that is a good question. Now, for the Devonian source, which we know was played a part in charging the McMurray, not as big a problem because it can get into the McMurray through direct routes. But Stephen, one thing that mapping shows you is when you actually, now I'm going to erase all these arrows, everybody, to answer Stephen's question. When you actually map oil and the porosity of these rocks, you have an oil-water contact that goes right across here. So there's less porosity and permeability in some of those Devonian units, but it seems that they were charged with oil and then bypassed oil, just like the other stratigraphy did. And it's the Clearwater Formation that's driving the bus. In other words, we treat the McMurray as a reservoir, Stephen, but the truth is, all of this is reservoir of some type. Just, it's not all good reservoir. Does that make a little more sense?
Yeah, no, that's good.
Yeah. Now from the class, any questions to follow that up? Okay, that's great. Now above this is the Clearwater Formation, and the Clearwater Formation definitely has oil in it. And I won't draw it in here, but there's delta and, well, let's just call it delta deposits in the Clearwater Shale that are not shown here, that are sandstone. And these are the Cold Lake, oil sands, right? That Imperial Esso is really drive. I mean, they've done most of the exploration and development in there. So there's Cold Lake. And then we have other units here. We're going to go to the Falher, which more than anything, we're going to call liquid rich gas play. That's a shore face deposit. The Falher is, just write that down, okay? And then above this, we get into ultimately the Paddy Cadot. And I'm just looking for the Falher here. The Falher basically comes in up here. So I'll have to draw it on the next diagram, sorry. But then it culminates in the Falher Formation, which is a shore face sand and has a lot of oil and gas in it. And so that's really the Manville part of the
Um,
stratigraphy.
sorry, would you just mind repeating that? I didn't get all of it.
Yeah. Sorry, can you ask the question again, please? Sorry, can you ask the question?
Yeah, sorry, I forgot to unmute myself. Just with the filare formation at the top, just not so much the one like you were just talking about like the last sentence ago.
Let me just be a little more clear because I kind of lost myself in that, really, Nick. So the shore face, the filare formation is in a shore face. It's more or less at the top of the lower Manville. It's a sandstone. And it's an oil and gas play that has, it played a pretty important economic role in Alberta that we'll get to at the end of this lecture, okay? And the flare formation in of itself is more or less at the top of what we call the Manville, which marks the Manville group is all of this stuff really. It goes from the Catamount to the Falare, the Catamount McMurray. And that really is our middle Cretaceous in a nutshell there.
Okay, that makes sense. Thank you.
Yeah, a little bit. And one thing you can sure start to see when you look at this diagram is that, you know, there's a real strong response to what the stratigraphy is, its composition, and sea level and tectonics, because there's a really complex relationship shown in this stratigraphy of tectonics and sea level that is a little hard to wrap your head around. And even if you know the stratigraphy very, very well in the Cretaceous of Alberta, it can be a challenge to make correlations from here to there sometimes. And it's certainly an interesting problem stratigraphically, okay? Now, we're going to go up section now, so we're going to continue the next section.
Oh, sorry. I'm just a little bit confused still.
Mm-hmm.
I don't know if I like missed it or something, but are you showing in the diagram that the filare formation like emerges again above all of that, or is
it was just unfortunately where they stopped this cross section, because if they'd included the filare, it would have included the whole group.
Oh, okay. So so the Manville group is everything below the filare in the diagram, but it also to the Catamount. Okay.
Mm-hmm.
Okay. Cool.
And the
Thanks.
McMurray. And I needed to add it there because I wanted to use it to anchor the next part of the diagram with the filare formation. And you'll remember on the second map I drew, the filare formation was a set of shorelines, which oversimplifies it a little bit, but it still serves our purposes. So that's a good oil and gas play. That ultimately gives way to shales of the Shaftesbury formation. And now I'm going to simplify the stratigraphy a little bit. So the Shaftesbury is another marine shale that interfingers with these shore faces of the Falare. The Falare formation, as we suggested above, was economically important. The Shaftesbury is related to that Dunvegan Delta that I mentioned. And I'm just drawing these as sand delta lobes that reach out and commingle with the Shaftesbury formation. So this is called the Dunvegan. Formation. Primarily a delta. Actually pretty well known in Alberta. Interestingly enough, even though it's big delta lobes and there's oil and gas exploration in it, it's pretty much normally been a disappointment to oil and gas explorationists because of of reservoir complexities and overall lack of good reservoir rock. That said, there's still plenty of exploration in it, and there's still a lot of oil and gas discoveries in it, but not really successful in the way the Falher formations or Cardium formations became. And then this commingles with the Cascapoo formation, shales again. And then going into the Cascapoo formation is, or above really, is that other shore face that I keep talking about, the Cardium formation. And the Cardium formation is one of these sandstones you can see in a few places in Alberta, because there's nice outcrop that buttresses the Bighorn Dam down by Nordegg. There's a good Cardium formation that forms the ledge that makes Bow Falls, Ram Falls in Alberta, and also very good fossil collecting there in the Colorado shales, which are co-mingling. With the Cardium formation. And the Cardium formation is it's present through quite a bit of Alberta. It's a nice oil play, certainly has been, remember Arnie Nielsen. And there we go. And it's a gas play too. And then ultimately we go from that to very simple terms, the Lee Park formation. The ocean evolves, or the shallow sea. This is another shale. And the Lee Park formation gives way to the Belly River, which is a sandstone, mostly fluvial and a deltaic. And it is played for oil and gas, but it's not the biggest deal compared to the Cardium or the Falher. And then this gives way to the Bearpaw formation, which is the last real shallow sea in Alberta. And ultimately the Horseshoe Canyon formation on top of that. And we really get the Edmonton group on top of that. But the Horseshoe Canyon, I'll draw as a sandstone. And almost everybody has seen the Horseshoe Canyon formation if you've gone to Drumheller, because the interesting stripy strata that's coal bearing there all around the town site and up to the Hoodoos, that's all Horseshoe Canyon formation. And now we've entered what's called the Edmonton group. That's part of the Horseshoe Canyon, but it goes, there's 4 units. Because we're in Edmonton, I'll do them all. Then there's the White Mud, which is right here in Edmonton and has dinosaurs in it. The Battle formation, the Schollard formation, which has the KT boundary in it. And that's the end of the Cretaceous then, right? And the next thing that we have is the Paleocene Pascapoo, which is mostly continental. But remember here, this is the last marine incursion Alberta would have. And if you've been to Drumheller, you'll even know that you can go to these extensive oyster beds and stuff like that and collect shelly material there. You can even see sometimes dinosaur teeth and dinosaur bones in it, but really the Dinosaur Park formation has most of the fossil finds that are easy to get. And I will remind you that you can always get away with stealing an oyster fossil, but you do not want to get caught picking up a dinosaur bone or tooth. It's the finest, really substantial. People get super mad at you. So that's the stratigraphy, hey? And throughout this, we're just evolving to shallower and shallower sea until there's no sea anymore. And now the sea has receded both towards the north and then towards Texas, presumably leaving everything like land in its wake. So where can you go to see these super cool things? Dinosaur Provincial Park is a no-brainer. Next week, I think on Monday, I have one of my master's students who loves Dinosaur Provincial Park. He'll give us a little virtual tour of Dinosaur Provincial Park and talk about what's cool about it from a geology and paleontology point of view. What we're looking at here are little hoodoos right in front of us. That's what these flat-topped little pillars are. And then you'll see things in the background here, such as a lithology change at that line. And what you're looking at is that white stuff is sandstone of a fluvial channel, and the brown stuff or gray stuff are clay stones that are related to the overbank deposits of that channel. So you're looking at distributions of siltstones, which are dark gray, and sandstones, which are light colored. And the whole story of Dinosaur Provincial Park is that of point bars, fluvial point bars, that are preserved in the rock record. And you can get a sense of that here. You see the stratification. It's not entirely horizontal, you see, and that's because it's really a point bar that's building out into a channel, mock paleontologist Stephen says you can commonly find mock paleontologists near the hoodoo selling oyster fossils, claiming they're dinosaur toenails. I wonder how much they sell them for. That's a great idea, man. Wish I would have thought of that. Okay, so these are fluvial bars. That's what we're looking at there. And I'm because we're going to get a closer look at all that and on next day. And then if you're going to do the Alberta geology thing, you pretty much have to go to the Joseph Burturel Museum. And nowadays you can go to the Philip Currie Museum up by Vancouver, Grand Prairie, Wembley, Alberta. And it's actually a good little museum. I've been up there and I really like it. And yeah, there's good fossil hunting in the area if you know where to look, but you got to know where to look. Joseph Burrell was a GSC guy. I mean, he was a Canadian, he was really a geologist, right? I think he was working in Alberta's Badlands in the 1880s. And he was, the Royal Tyrrell Museum was named for Joseph Burr Tyrrell. And he started out working, don't go out, son of a bitch. I'm out of batteries here, hang on. Just fix this up. I might have to do this. Just stand by. But yeah, Joseph Tyrrell started as a lawyer while working in a law firm. I actually don't know. I'll get back to that. He was working as a law firm, and a doctor advised him to get a job outside for his health because he wasn't doing that well. And so he got a job somehow with a geological survey and came out west, and he did a lot of paleontological work with dinosaurs and whatnot. And he ended up being quite famous. My computer's just rebooting here. Sorry about this. I think it's still rebooting. That's okay. There we go. All right. Now let's see if this is going to work. Oh yeah, I came back to life. I'm really impressed. Okay. Yeah, so the Tyrrell Museum, go there, okay? And then there's people who are associated with the Alberta dinosaur business back in the day. Stephen adds a note here that at an antique show, a fellow tried to sell him a dinosaur long bone, but when he looked at it, it was a big ammonite XD, big, what is a, oh yeah. But I mean, yeah, these great ammonites, even better. I'd rather have a big ammonite than a stupid dinosaur bone. That's what I think. Laughing face. Lawrence Lamb. Lawrence Lamb, he was a Canadian geologist. He worked in the 1880s all the way up through to World War I, looking at dinosaurs in Alberta. He's had dinosaurs named after himself, like Lambeosaurus. He did a lot of exploration. He wrote several papers for the Geological Survey of Canada. Just loaded up an example for you here. Where you can actually see that he's describing the hadrosaur Edmontosaurus from the Upper Cretaceous of Alberta, and then there's some nice pictures in here. Oh, look at the publication date of this, 1920. That's pretty cool, eh? We can just page through this, just stand by. So this is a drawing that he made of the hadrosaur, line and some stipple work. Pretty amazing. They often had artists doing their work for them, and sometimes they had to do it themselves. A lot of paleontologists were quite artistically inclined, line drawings showing the features and sutures of the shell and so on. So I always love this type of work. It's so creative and artistic. That's a photograph, but this is the hadrosaur Edmontosaurus. I can put it on E-class if I remember to, then you can have a copy. But I think I actually did already. You might want to check that. Okay, so that's Edmontosaurus, and that is Lamb. And then after there's Barnum Brown. Barnum Brown was a paleontologist. He was referred to as Mr. Bones. He was an American paleontologist, and he was named after P.T. Barnum, the circus person. So that's pretty wild. He discovered the first documented remains of Tyrannosaurus, which pretty much sent him on his way to fame. And the Tyrannosaurus that he described is still one of the most famous fossils ever found to this day. He collected a lot in Montana in an area that was called the Hells Creek Formation. I think it's called Hells Creek, but ended up coming up to Canada in the 1910s, and definitely spearheaded a lot of exploration in Alberta. But the big one in Alberta is Charles Sternberg. We have extensive collection of Sternberg fossils and copies of Sternberg finds in our own museum collection here. The Royal Tyrrell Museum is absolutely full of Sternberg collections, and his whole family was involved. This is Charles Sternberg here. This is Charles Jr. here, who became actually the only truly educated professional paleontologist in the family, and then the other sons, George and Levi, but they all collected and sold fossils. And they did this for the British Museum, the Natural History Museum in San Diego, the museums in Eastern Canada and Eastern USA. And basically, you can't really talk about vertebrate fossils in Western Canada without acknowledging that Sternberg's played the largest role in all of that. And it'd be impossible to frame the context of dinosaur paleontology without discussing them. Another cool place to go is Writing on Stone Provincial Park, where you can actually go look at the Milk River Formation. And that reminds me, there's something I wanted to show on our stratigraphic picture that I didn't. Sorry, I'm letting my tablet charge here. So I'm showing you everything that's kind of coming in from the west, but from the southeast, right at about this stratigraphic level here. So we've gone back to the stratigraphy. I forgot to add in the Milk River Formation. And the Milk River Formation is important economically in Alberta because it has one of the largest gas fields in the world in it, and that's called the Alderson gas field that straddles Alberta and Saskatchewan. So the Milk River Formation comes in there, and it's cool in that you can actually see it in outcrop, and that gets us back to Writing on Stone Provincial Park. Writing on Stone Provincial Park is all fluvial deposits associated with the Milk River Formation, and has a lot of really interesting reservoir quality sandstones that are exposed there. And a lot of geologists actually go to Writing on Stone Provincial Park to make observations of the outcrop that they can apply to subsurface reservoirs so they can better exploit it for oil and gas. In the case of Milk River, really gas more than anything. So yeah, go to Writing on Stone Provincial Park. Unfortunately, it's just a stone's throw from the US border, meaning it's a heck of a drive, but it's one that's totally worth it. Once you've gone that far, then you can go see those cool little volcano mountainy things. Oh, what are they called just into Montana? Stephen, do you remember? You go south from Writing on Stone, and there are those highlands that are just to the east when you're crossing the border.
Yeah, no, I know the ones you mean. I don't remember.
I know. They're so fantastic, and I can't remember it. I'll come to class with it next time. Never mind. I could cheat and go to Google Earth and look right now, but we'll leave it at that. Now, we've been talking a lot about river deposits and marine deposits, and not much when we talk about Alberta in the way of volcanics at all. And in fact, we haven't talked about volcanic rocks since we were basically looking at Precambrian rocks, right? That's the only volcanic rocks we've discussed in Alberta so far. But there are Cretaceous volcanics called the Crow's Nest volcanics. And if you ever came on our field school in Alberta, then Stephen and I would take you to the Crow's Nest volcanics near Coleman, Alberta here. In the Coleman, Alberta, there's Coleman, there's Blairmore. Our field school stays there. Turtle Mountain's just right over here. And the Crow's Nest volcanics are definitely related to ejecta that are associated with the volcano and its pyroclastic flow deposits, although it seems to be sedimentologically more complex than that. Anyway, it's quite extensive through this area here, although I've never really looked closely at the Crow's Nest, but Stephen has, and I don't know, do you want to say anything about its distribution, Stephen, or anything like that?
It's not widely distributed. In fact, it seems to be preserved within a single thrust sheet. And if you go into the main thrust sheet beneath that, beneath Turtle Mountain, there's none of these volcanics. And if you go above into the Lewis thrust sheet, you don't find them there either. So it's a very strange package of rocks. Kind
of a little baby volcano or something.
Well, the formation extends, I don't know, about 100 kilometers along strike, and is 300 to 400 meters thick, I think, at its thickest. So it's
pretty
still
thick.
Yeah.
Yeah. I find this depositional model that Musu and Nelson presented interesting because they have it coming out of a shallow sea, but there's actually not much in the way of shallow seas right in the area at that time. It's more dominated by little rivers and stuff like that. So I'd take this depositional model with a grain of salt in any case. Not that it matters, right? I think if Dawson goes back to grade school and teaches kids this, I'd be fine with that. And then this is what the rock looks like. And this is why people like the Crow's Nest volcanics. It's garnetiferous volcanic rock, and you have features in it like these dark minerals that are black garnets. And I can't remember the mineral name, but Stephen will definitely remember the name of those black garnets. Maybe Maya, who's visiting, will too, but that's a bit of a test.
Well, the various names, it's an androditic garnet, but because it's black, it tells us that it's titanium rich, and I believe they're called either melanite or melankite.
Okay, cool. And then we even have examples of the Crow's Nest volcanics in our museum here. So you can go down to our museum and look at the Crow's Nest volcanics. Pretty awfully nice rock when you're used to looking at sedimentary rocks. And then an area where you can actually go visit the Cardium Formation, and that's at Ram River Falls. And you might guess that this ridge that's actually forming the escarpment that the falls flow over is actually the Cardium Formation sandstone. And if you look in the shales above and below Ram River, but particularly above, you can find beautiful ammonite fossils in these areas. So Ram River Falls is good. It's a little bit remote-ish. Not that many people go there. So that's a good place to visit to look at Cretaceous rocks, that's for sure. And then the Catamount Formation, which is one of the lowermost units in the Cretaceous, is present quite often in the foothills and the mountains. And the Catamount Formation we actually see in the same area. It's very closely associated with Crow's Nest volcanics at Blairmore. You can go to Jasper and see the Catamount Formation. This is a ridge right by Blairmore, Alberta, where we took students on field school, and there's the conglomerate itself. You can see it forms these pretty little ridges that are quite mappable and walkable, and you can follow them along. They're very cool. And there's examples of the Catamount Formation at Elbow Falls as well. So you can go look at the Catamount Formation there, and it's worth seeing it. And I'll just add that the Catamount Formation, or the Catamount area in Alberta, is a great place to go visit Cretaceous rocks that are about Catamount and a little bit younger in age. There's a few different strata there, but there's also beautiful Devonian rocks. This is, for example, off in this area here, that's a quarry of Palliser Formation Devonian limestone that they quarry for cement. There's an abandoned railway track that goes along this valley here that you can hike along quite readily, and it follows beautiful outcrops going all the way from the Devonian all the way up to the upper part of the Middle Cretaceous. So you have all of this stratigraphy so conveniently located along this abandoned railway line in this beautiful area that you can hike along. So, you know, now, since most of you have some expertise in rocks that are Devonian, Mississippian, Triassic, there's Triassic rocks here too, and Cretaceous, you can go there and see all of these rocks and the fossils that are with them. So that's worth doing. Now, you had a 1 hour asynchronous lecture this week, and we're going to take Friday off. And Maya, don't worry, I'm going to let you present next, so we're good. We're going to take Friday off this week to go asynchronous by reviewing all of your peers' PowerPoint presentations. And I'm going to give each of you a little scorecard to fill out so that you can give me some feedback about your evaluation of their presentations. It doesn't have to be done by Friday, but I'll ask that you be done that by Sunday or something like that. And I will try to give you some looking forward viewpoints of the exam on Friday and stuff like that. So tomorrow, I think I'll give you some information about how the class is going to go the next 2-3 lectures. But Friday, we're going asynchronous. We're going to review our peers' PowerPoints and take some notes, because those are part of your examinable materials. And there's actually 20 of them. So it's going to take you the whole 2-hour lecture to go through all of those materials. And I have to go through them too. I've only looked at 4 so far, but I loved them. I thought they were great. So well done. Now, on that note, Maya Lagrange is a PhD candidate in our Department of Earth and Atmospheric Sciences. She's an outstanding young scholar. She works on the geochemistry, sedimentology, and geology of the Canal Formation, which is a formation that has some economic significance in the far north. And Maya's going to give us a presentation today, but not on her PhD. She's going to give us a presentation on the geology of the Okanagan area from a recreational point of view, because that's where she initially is from. So Maya, do you want to finish my introduction of you?
Sounds good, thanks. Yeah, so I guess this isn't, so like Maria was saying, my thesis is focused on a black shale that's the equivalent of Devonian black shale in the Northwest Territories. So what I'm going to be talking about is not really in my wheelhouse in terms of what I'm studying for my PhD, but when Murray asked for when he asked for volunteers to maybe give some presentations on the geology of some of the parks in Western Canada, I thought it would be a nice idea to talk about the Okanagan because it is such a popular vacation destination for people in Western Canada. I thought it might be nice to have a little bit of context on what you could see or maybe have seen if you've been there or if you're going to go. So I'm sure some of you know the Okanagan is known for its vineyards, for its wineries, water sports, things like that, better weather than Edmonton. Anyway, so I'll just try, go through a short presentation on it with, the main goal is just being to talk about what you could see when you're there and maybe some places that you could go to see some of these rock types. So I will share my screen now. Go to desktop, share. Is it working? Right?
Yes, it looks great.
Okay, so we'll just start going through the PowerPoint. All right, so, all right. So, as I'm sure many of you know, the Okanagan Valley is a fairly sort of elongated valley in the southern British Columbia in Canada, near the Canada-US border. And moving on to, so zooming in a little bit, the Okanagan Valley has the Lake Okanagan, which is sort of a long and narrow lake that sort of winds through the valley. And the biggest, city in the valley is Kelowna, and there's also some smaller ones, Vernon, Penticton, places like that. So starting to dive into the geology of the area, looking at where the Okanagan Valley sits in terms of the geologic belts of BC. So these are belts that have similar geologic histories and sort of represent accretion of terrains onto the North American Craton. And so the Okanagan Valley basically sits in between the Omoneka Belt and the Intermontane Belt. And so basically for this presentation, I'm going to go through a simplified geological map of the Okanagan Valley and just go through the different sort of broad rock types that are present and where you could maybe go to see some of these. So as you can see, just looking at this geologic map here, you have the Lake Okanagan running sort of north-south, and Kelowna is here. And then this just shows the distribution of some of the different rock types on the maps. This is a fairly simplified map, but it'll work for this presentation. And I'll mainly be talking about igneous and metamorphic lithologies in this presentation for the reason that the sedimentary cover in this area is much less extensive than in the Western Canadian Sedimentary Basin. Most of the sedimentary cover is quaternary and is alluvial or glacial lacustrine. So because it's not dominant, this presentation will mainly focus on the igneous and metamorphic lithologies. So I'm going to start by focusing on this purple unit that you can see to the east of Lake Okanagan here, which is basically the Okanagan complex of gneisses. Ages for this unit have been proposed from Precambrian to Eocene, so fairly wide range. So this unit is primarily gneiss, so high-grade metamorphics. Here's an example you can see from Munson Mountain, which is near Penticton. And so I'll just go through a few places that you could go if you wanted to see some of these gneisses. One place that I think is pretty cool in the Okanagan, it's not too far from Kelowna, probably about, it's like a 20-minute drive down the logging road to get here, are the boulder fields. So these are basically mass wasting deposits and with nice boulders. And so you have to excuse the iPhone quality, but I'll just play this video for you here on the right where you can just see some, see sort of what it looks like. And so a lot of people go there for bouldering, for climbing, but there's also a lot of nice trails that you could go there to see the gneisses. And I'll also just show you another location that is common that people visit. So I'm switching to Google Earth and I'm going to try going through this presentation. So here on the east side of Lake Okanagan, where the metamorphic gneisses are mainly present, are some of the places I could suggest going to see, that you could go to see them. So first, I guess in this presentation is Canyon Falls Park. It's also called Crawford Falls. It's really not far from Kelowna. And maybe if we go into 3D, you can see a little bit that it's a canyon that has sort of been carved into the gneisses. And there's a waterfall that people go typically on to see. A lot of the gneiss here would be covered by moss, but in some areas along the hike leading up to it, you can see the lithology. And then another cool area would be the boulder fields. So I showed you some videos before, but it's not far out of town. This photo sort of shows you. So there's some very nice trails along there that you could go to. So those are the areas that I wanted to show in terms of the metamorphics. So moving to another lithology on the map, so focusing on this, the oranges. So there are quite a few volcanics in the area. They're mainly felsic volcanics, so rhyolite, dacite, andesite, things, those types of lithologies. Here's a picture. It's not from the actual area, but just of dacite, in case you would like a reminder. So in terms of where you could go to see some of these lithologies, there's a few different places. I'll show you on Google Earth. Layer Cake Mountain, I think, is the most interesting in my opinion, but there's a few different options. So moving on. So yeah, there's definitely some volcanic mountains in the Okanagan area. Mount Boucherie is one of them. It's also, it's in West Kelowna. It's a common hike that people do. It's not far out of the city with some nice views, but there's definitely some weathered volcanics there. Similarly, Giant's Head, which is in Summerland, is a similar volcanic feature, once again, that people commonly do hikes there. And then you also have Knox Mountain. I'm not sure if any of you have been there. It's a common spot that people visit in Kelowna. And this is also an area where you could see some weathered volcanics. But as I was saying, I think the coolest of any volcanic feature that I have seen in Kelowna is Layer Cake Mountain. And so this mountain, as you can see, is might originally look like, or from a distance, it looks like these might be sedimentary beds. But this is actually dacite, so it is an igneous, this is a volcanic feature. I think there's some of the studies that have tried to explain this layering have proposed that the layering developed from crystal fractionation during cooling, followed by contraction, and then differential weathering of some of the layers, making them even more prominent. But anyway, that's a pretty cool feature with some nice hiking trails along there that you could visit. And all right, so who's next? So next, focusing on this pink rock type in the geological map, which are plutonic igneous rocks. Once again, I don't have a photo actually from the Okanagan, but they're mainly granitoids, so also felsic, typically granites in the area. And if you're looking to see some of these deposits from these igneous intrusions, somewhere you can go is called Trout Creek Canyon, which is basically a canyon that was cut into one of these igneous intrusions, and I will just pull that up also on Google Maps. It's a neat walk because it has one of the, it has a railroad trestle bridge that goes over top, and you can go walk across that and look into this canyon, this granitic canyon. So finally, the last feature I wanted to talk about on this map is this detachment fault that runs through here, so which is basically a low angle normal fault. And this fault basically explains why you see this juxtaposition of lithologies on the west side versus the east side of the lake. Here you have an abundance of metamorphic, so this Okanagan gneiss complex, whereas in contrast on the west side, the lithologies are dominated by volcanics and plutonic rocks. So yeah, the fault basically explains that, and I'll get into it a little bit more in a diagram of the next slide. But some of the features that you can see that are indicative of this deformation are pegmatites with folds that have their axes parallel to the direction of extension, and some granites that have been metamorphosed, gneissic granites. And so just to explain that a bit more with the cross section, we have, so this is a cross section that was taken 18 kilometers south of Penticton. So going back to this map, you see Penticton here. So this cross section would fall somewhere in here, going from approximately east to west. And so the detachment fault runs along here, and basically this fault has had movement of the upper block or hanging wall downwards relative to the lower block or footwall, resulting in exposure of the exposure of gneiss on the east side due to erosion, whereas on the west side, because it was at a more of a low, there's still the volcanic and sedimentary cover present. So that sort of explains the differences in lithology on the east versus the west sides of the Okanagan Valley. And finally, I just wanted to end on sort of a different note, but just tying in the geology of the Okanagan to one of the main things that it's known for, which is its wine industry. There actually, when I was doing some research on the geology of the area, I was surprised by how many papers that I came across that were similar to this one here. So basically, papers looking to see at basically looking at the influence of the geology on the wine, because it influences the soils. So for example, this paper that I put up here was looking to see if you could use trace metals to determine the vineyard that different wines came from. I think they had mixed conclusions, but anyway, I just thought I would end with that, tying the geology to one of the main industries. And that is all. Sorry, I missed some chat stuff. Oh, Blair Murray says, I like layer cake man.
It's awesome.
It is cool. I think it's my favorite thing.
It looks delicious too.
Yeah. Anyway, this is a view from Knox Mountain that I just thought I would end with. It looks delicious. Yeah. It's pretty cool. Anyway, does anyone have any questions? How do
I've lost my chat. Let's see.
Me too.
There it is.
How do I?
Okay, no questions so far.
Okay. Well, thanks for letting me talk about this. Thanks.
Yeah, well, I really appreciate it. I thought that was good fun, a good adventure. And if you email me the slides, I can put them on their hiking guide for them.
Sounds good. Yeah, I can also email the Google.
Okay, that sounds good.
Thanks.
Yes, hello? Oh, okay. Nick says, very cool, like the cake. I thought I heard somebody ask a question, but I must have been hearing things. Ashley says, thank you, Maya.
Thank you.
I threatened to her that we were going to play Bohemian Rhapsody on Wednesday for last week, because she plays such an important role.
Wait, when did you say we were going to play it?
Wednesday, and end of class.
Oh, okay.
Mm-hmm. See you, Jax. Bye, Margaret.
All right, sweet.
Okay. All right, you all can start logging out, I think. I'm just, oh, the other thing you could do, Maya, is you could send me the PowerPoint slides, but if you can download those KMZ files or whatever they are too.
Yeah, I downloaded it.
Okay, that sounds great for some reason. Okay, that sounds good. Just email me those then, and thank you very much.
Yes, thank you.
Okay. All right, let's see. So I'll send out some clear instructions about the synchronous materials and their relationships to the exam and how the exam will look tomorrow. Okay, everyone? I've been kind of going hard this week, so I'm a little behind on those things, but we'll do that.
Hi, I just had a question about the notes real quick. I was just thinking about it before we were going over it, but with the cross sections, like the one that shows like the Precambrian up to like the Upper Cretaceous, I was just wondering where Edmonton would be in that, as well as the one below it as well, where it's like the one where you went over like the oil in there.
It's a good question. Now I'm going to tell you, it won't be on the exam because we went there already.
Yeah, I know.
But it's the right question to ask for sure. And here, I just have to share the screen. Oh, actually, you know what? I can do it right on here if I open those notes on my other computer. Just stand by.
You know, I doubt there'd be another like rephrasement of the question for the final, but I just want to. Knowledge know where it is. Yeah.
Even more reason to ask, Nick. Even more reason. Okay. Well, you remember. You actually have a hint to the answer of this in your notes, because you'll remember when I said, okay, let me share the screen. I love questions like this where you don't know you know the answer already. Okay, now, do you see the Alberta cross section?
Yeah.
Okay, good. And do you see my cursor?
Yes.
Okay, now you'll remember I showed you a map in the Mississippian that showed you the subcrop edge of the Mississippian, right? Do you remember what the subcrop edge means? It's the erosional edge, right?
Mm-hmm.
Okay, and remember on that map, Edmonton was just outside of it, meaning Edmonton is actually right whoops, right here in the stratigraphy. You see that?
Okay.
So Edmonton's just right outside that. And if you have that Mississippian map that shows the subcrop edge of the basal Mississippian is really useful, because so if you drilled an oil well here, you should go arguably straight from the Manville into the Devonian, the uppermost Devonian.
Yeah, and that has to do with from the midterm where it was like the Permian and all that's only found west of Edmonton.
Yeah, well, in particular, I used the same dirty logic on you as you had two maps in your notes. One showed the extent of the Ordovician outcrop was clearly limited to the deformed belt, and the other showed that the Precambrian strata was clearly limited to the deformed belt. And those were in those respective lectures, the Precambrian and the Ordovician. So I didn't give you full marks if you showed the Devonian and the Ordovician and the Precambrian going all the way under Edmonton, when we'd made it kind of clear that they were limited to the mountain belts. That's all. It gave me an opportunity to make an easy looking question hard, which is the dirtiest trick in the book, but it's kind of where you have to go with open book exams, right?
Yeah, for sure.
Yeah.
Yeah,
Go ahead.
sorry, with the next cross section, sorry, it would be, I don't want to say around the center of it, or
Okay, I'm not even sure I can answer that.
because the McMurray formation.
This is showing here. Oh yeah, I can answer that. I mean, so then Edmonton ends up being right around here. Do you see my cursor still?
Yeah.
Yeah, it's right around there.
Okay.
Yeah, but I mean, remember, this cross section is very variable as you go north to south. So in the absence of really knowing where this cross section is taken, that can be a pretty abstract question, because Edmonton may well not be on that line of section, right? Which is why I would ask you to tell me what's below Edmonton rather than the other way around.
Where Edmonton is on cross.
Yeah, for sure.
All right.
Yeah, all good questions, so, and you're thinking about it the right way.
Okay, and then the next question, like another question I had was, I know you brought up the Boreal Sea, and then you brought up the Bear Paw Sea. Does it just like change names over time as it like changes shape and like extent?
Yeah. Even after the Boreal Sea reaches while the Boreal Sea is coming down from the north, then from the Gulf of Mexico, that seaway is coming up to the north towards Alberta, right? And by the time they actually meet in the middle and commingle, they're referred to as the Western North American Seaway or something like that. So they're not referred to as the Boreal Sea anymore. And then we tend to call most of these seas afterwards, after the shale intervals, they're named after the Bear Paw Sea, the Lee Park Sea, the Cascapow Sea, I can't think of the one that's related to the Cenomanian, the Shaftesbury Sea. So you tend to think of it in those terms. They're all informal names. Boreal Sea is more formal in that it's used quite often in the literature. And so is the Western Interior Seaway. That's a formal name, right? But the Lee Park Sea, for example, is not adopted really in wide use in any way.
Okay. And another thing just on the side is, before I came to Edmonton, I actually lived in Drumheller.
Oh, good.
And yeah, so I have to, with all those notes of like, what's the term? I don't want to say fake paleontologists, but there's a lot of like amateur fossil shops all over the place, especially in the summer.
Absolutely. And almost anywhere you go where there's lots of fossils, you'll find the same behavior. And people really love fossils. It's interesting how fascinated they are with the remains of ancient life. It really blows my mind. I find the excitement people have over fossils to be really exciting, but it does make it an exploitive industry. For example, if you go to Morocco, I traveled there when I was quite a long time ago. but you know, any market in Morocco is, they sell fake fossils that are really well done fakes for very good prices. So it's pretty easy to separate yourself from your money with a fake fossil in Morocco, right?
I mean, even in Drum, it's like some of the prices they had for some of the like fossils they had. It's like it's just ridiculous. I know there was when I went to Banff one time. There's a fossil shop there, and they had all these sort of things on display, and then they had like, of course they show price tags, but of course no one's gonna buy that sort of stuff because it's like
Right.
no, like, so people are fine with going like $50, but no one's gonna see like, I think they had a mammoth tusk there or something. It was like 3,000
Oh yeah.
or something like that, but it was like,
But
yeah,
look
it's
at
just funny.
that Tyrannosaurus that sold for $3 million, right?
Well, yeah, and that's because I want to say it's got a little bit more of an infamous sort of thing to it. Like it's a little bit more well known, whereas if you're trying to sell obscure,
You know, I agree, but I've got a friend who's made a perfectly good living selling trilobite fossils for the last 20 years, and he makes enough money to live off of no problem at all. So he just buys and sells trilobites on the internet. That's the only type of fossil he'll touch is a trilobite, and he makes about 80,000 a year doing it. So,
and
probably it's mostly tax under the table because he's a crooked son of a bitch anyway. So it's, yeah, for sure.
no, that reminds me. There was I don't remember how long ago it was, but PBS Eons. I do watch a lot of it besides the course, but they did a video on that sort of stuff and how paleontology ties a lot into, like, I don't want to say the black market sort of fossil trade.
Oh, absolutely.
Get a
Phil
lot of those
Curry gives
specimens.
wonderful talk about that and stolen fossils from Mongolia. If you enter the paleo program at U of A, you're bound to see that presentation.
I think that's what it was on actually. It was, I forget the name of because of course it was only about this one creature's fossils. I think it was like it's like Dinokairos or something like that.
Okay, yeah, that sounds familiar. All right, yeah.
But no, it's a lot of, it's interesting how that ties into it a little, in my opinion.
Yeah, absolutely true.
All right, well, I guess see you Monday, right?
Yeah, hey, take it easy, for
Yeah,
sure.
you too.
Thanks for showing your face, Nick.
Oh yeah.
All right, and by page, okay. All right, so great. Thanks, Maya. Really good job. I know so little about the geology of the Okanagan that I thought that was super useful. I mean, I actually want to go see Layer Cake Mountain now. I'm pretty excited to do that.
Yeah, it was a good refresher on a few things for me. Anyway.
Stephen, you must have taken you Vic kids out to Layer Cake Mountain or something.
Yeah, I've never been on Layer Cake Mountain. Have to go there sometime.
Yeah. Because it looks cool. I'll give it that. A Dayside Mountain, I'm in. But yeah, very well done. And I appreciate the help because, you know, I find these 2-hour lectures actually really hard to deliver. I peter out after 50 minutes and there's just no gas in the tank anymore.
Yeah.
So having that little bit of extra help makes a huge difference.
Yeah, cool. Well, yeah, thanks for letting me talk about something different.
Okay. No worries.
Okay.
All right.
Bye.
Bye. See you, everyone.
Good night.
Okay, take care.
See you, Marie.
Bye. Thanks, Stephen, for visiting.